Hello everybody, I am Guillaume Gamard and I'm going to talk about Rice-like theorems for automata networks. This is joint work with my friends Pierre, Guillon, Perrot and Guillaume Theyssier. An automata network is basically a graph, a directed graph like this, in which each node has a state that is chosen among a set of possible states and that evolve with time according to the current state of its inbound neighbors. So the edges of that graph represent the flow of information, and node number 3, for instance, will evolve in time by reading the colors of nodes 4 and 2 here. All evolutions are done synchronously and in parallel, so that is similar to what happens in cellular automata. So in this example, each node has the same set of possible states, the three colors here, red, green, and orange. And three of these nodes have exactly one inbound neighbor, and these nodes evolve according to this transition function represented here, while node number 3 has two inbound neighbors, and it evolves according to these rules here that basically say that if both neighbors have the same color, then 3 is going to take that color as well, while if the neighbors have different colors, then 3 is going to take the last remaining color here. So the model evolves in time, so here is one step of evolution, here is another, and so on and so forth. And there is no specified initial configuration of the system, and there is no halting condition either. So the system just runs over time forever. And for now, that model is deterministic, so we have update functions. Each configuration has one possible future. Automata networks were introduced in theoretical biology to model gene regulation networks. The fact that when a gene expresses itself, it may boost or inhibit the expression of other genes, and that in turn can have effects on yet other genes, and so on and so forth in a whatever fashion like that. But it also occurs in engineering. Say we have an elevator with different microcontrollers that need to communicate with each other, and more generally in distributed algorithms. But until, quote, recently, so the 70s or the 80s, there weren't that many general studies of automata network per se. There were mostly papers about specific applications of automata network and specific problems for those applications. An interesting point that automata networks share with cellular automata is that very simple networks may have very complex dynamics. And actually the general philosophical question is what is needed in an automata network to get complex dynamics, to get complex behavior. But the stakes are lower than with cellular automata because in a given network we have a finite non-changing number of nodes, and each node has a finite number of possible states. So this means that the set of possible configurations of the system, I mean global configurations, is finite. And therefore, all interesting questions about automata networks are decidable, because in the worst case, you can take your network, enumerate all the configurations, and test whatever you have to test on your network. But of course, performing an enumeration of all the configurations might take a lot of time, and so the idea is that we like to have faster algorithms than that to test interesting properties of automata networks. On the other hand, the Rice theorem is about Turing machines, and it states that every non-trivial property of the function computed by a Turing machine is undecidable. So assume for simplicity that each Turing machine computes a function from the integers to the integers. Well, it is, for instance, undecidable to test whether the function computed by a given Turing machine is increasing, given the transition table of the machine. We'd like something like that, but for automata network. However, as I just explained, all interesting questions in automata network are decidable, so we cannot have strictly in a Rice theorem in the strict sense of the term, and rather we'll have results along the lines of any non-trivial property of the function computed by an automata network is hard. Hard meaning, for instance, NP hard or maybe P space hard, but a complexity lower bound here. So this is far from being a formal statement. So we need to explain what is the function computed by an automata network, what is a property on that function, and what do we mean by non-trivial and by hard. And these two will have different meanings in different theorems. We get various trade-offs of what we require for something to be non-trivial and what we get as a complexity lower bound. So first, what is the function computed by an automata network? Well, it is just the function of the space of global configurations of the network to itself. So capital Pi here is just the set of possible configurations of my network, and f is a global function from capital Pi to itself. That is just the function that performs one step of evolution in my system. And the transition graph of f is just the graph of that global function. So it is the graph where nodes are configurations of the system this time, and edges are just transitions, are just steps of evolution. So do not confuse the transition graph with the interaction graph, the visibility graph that we saw on the first slide. The transition graph is much bigger. It is actually exponential in the size of the interaction graph. And since our networks are deterministic, the out degree of the transition graph is 1. Each configuration has exactly one next configuration, one successor. So for illustration, here is the transition graph of the automata network that we saw on the first slide. Each node here now represents a configuration of that system. There are 4 tiny digits that represent the 4 colors of the 4 automata of the system. And each edge is a transition. So for instance, that configuration transitions into this one, and this one transitions into that one, and so on and so forth. And since we have finitely many possible configurations, global configurations, and we have determinism, for pumping reasons, any configuration will end up in a cyclic evolution if we wait long enough. However, those cycles might be very, very long. They may have exponential size in the size of the network. Now, what is a property? For now, a property is anything that we can express in first-order logic with variables ranging over configurations of the system. So there exists x such that blah 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 means that there exists a configuration x such that blah blah blah. We have a symbol t of xy that means the configuration x transitions to the configuration y. We can test equality between configurations, we can take negations, we can take conjunctions, and all the missing usual symbols, universal quantifier, disjunction, etc., are just macros that can be rewritten with these ones. And this language is rather expressive. For instance, we can write formula to ask whether a network is injective, meaning that each configuration has exactly one predecessor, whether a network has 3 cycles of configurations, each having length 5, or whether we have at least 7 nodes with 4 predecessors each. And all of these questions are credible questions in terms of applications, especially in biology. We need to remove so-called trivial formulae. So what is a non-trivial formulae? Well, formally speaking, a formula is omega non-trivial if and only if it has infinitely many models and infinitely many countermodels. But there's a twist. Here, a model means an automata network whose transition graph satisfies phi, and a countermodel means, well, an automata network whose transition graph does not satisfy phi. It is not the same as having infinitely many graphs that satisfies your formula and infinitely many graphs that do not satisfy your formula, because some graphs are not transition graphs of any automata network. At the very least, to be the transition graph of someone, you have to be of out degree 1, because the networks are deterministic. So we actually want infinitely many automata networks whose transition graphs satisfy phi, and infinitely many automata networks whose transition graph do not satisfy phi. And that is the condition to call a formula omega non-trivial. And the main result of this talk is that to test whether an omega non-trivial formula phi is true or not in a network is either NP-hard or co-NP-hard. So more precisely, we fix a formula phi that is omega non-trivial, and we define the problem phi dynamics, which is we take as an input a deterministic automata network F, and we have to answer whether the transition graph of F satisfies phi or not. And that problem is either NP or co-NP hard, and that depends on the formula phi. This calls an important question, that is, how do we encode an automata network to give it as an input to an algorithm? It turns out that this result is sensitive to how we encode things. And the natural encoding for automata network is to give the interaction graph, the visibility graph from the first slide, and then for each node to give the update function as a Boolean circuit and not as a transition table. The reason for this is that you have to think of automata network as networks of computers that each run a program that might be different between computers and that sometimes communicate with each other. And under those circumstances, what we get as an input is the source code of the program run by each computer. And this way to specify inputs is also credible for biology. They usually do not have a full table of influences of genes between each other, but they rather have things like if that gene and that one do this, then we get that result, and so on and so forth. So that is how we encode automata network as input for algorithms all the time. I want to insist a lot on that the formula phi is not a part of the input for this problem. Only the automata network is. And the omega non-trivial condition that we have in this theorem is actually optimal in a sense. Because if phi is an omega trivial formula, so something that is not omega non-trivial, then this means that, for instance, the number of positive automata network is finite. And then the phi dynamics problem here becomes testing whether the input belongs to a finite list of possible inputs that is fixed in advance. And that is not an interesting problem. That can be done in constant time because the list of positive inputs is fixed in advance. So omega non-trivial is the best thing we can ask here. There is a natural variation of that question because I insisted a lot on that phi is not part of the input. One would naturally ask what happens if we make phi part of the input. And in that case, the same problem becomes p-space complete. So if we receive as an input a formula phi and a deterministic automata network F, and we have to decide whether its transition graph satisfies phi or not, that new problem is p-space complete because now we depend on the formula phi. And the proof is a classical reduction to the QBF problem. So those were results about transition graphs, but in automata networks and in dynamical systems in general, we're also interested in the long-term behavior of the system. So intuitively, when we start a system, it will do some transient things that we are not really interested in, and at some point the system will go to its cruise regime, and then it will have a long-term behavior, and we're only interested in that long-term behavior. And we also have hardness results in that context. So first I have to define what a limit configuration is, and intuitively a configuration is a limit configuration if and only if it is visited infinitely often in at least one execution of the system. So that's a limit configuration, something that's visited infinitely often in at least one run. The limit set is the set of limit configurations, and the limit dynamics is the subgraph of the transition graph that is spanned by the limit set. So as long as f is deterministic, which is always the case so far, the transition graph has our degree 1. It has this very specific shape that I've shown a few slides ago, and therefore the limit dynamics of such an automata network is just a union of cycles. The previous theorem about testing first-order formulae generalizes to limit dynamics. So if phi is an omega non-trivial formula, then testing whether the limit graph of a given automata network satisfies phi or not is either NP or co-NP hard. And the proof ideas are the same as in the previous result. But since we've restricted ourselves to limit configurations, we have this very specific shape of the limit graph as a union of cycles that I just explained, so we'd like to do more than just first order. And one thing that first order cannot do well is counting configurations. And it turns out that counting how many limit configurations a given automata network has is a question that makes sense, especially in biology. So, for this slide, I'm going to work on a Q-uniform automata network. So an automata network is Q-uniform if and only if each node has exactly Q states. So all the nodes have the same number of possible states, and that number is called Q. And now I'm given as an input still an automata network, still encoded the same. But the question intuitively is, do we have many limit configurations or not so many? And the formal definition of many is actually chosen by u. So you fix a function lambda that takes two integers and that returns an integer and that satisfies these bounds. And what we call having many limit configurations is if we have more than lambda qn limit configurations, where q is the number of possible states for every single node, for each node, and n is the number of nodes itself. So lambda is a definition of, quote, many limit configurations. You choose it between these bounds, and the problem of given a deterministic Q-uniform automata network F, testing whether it has more than lambda qn limit configurations or not is p-space hard. But there is a contrasting result, because here the lambda qn function is required to be bounded by some exponential that do not depend on q. And it happens that if we want to test whether an automata network has every possible configuration that is limit except maybe a polynomial number of them, so formally if we have delta a polynomial and we fix lambda being every possible configuration minus that polynomial, then the same problem, lambda limit size, is, quote, only in the sigma 3 level of the polynomial hierarchy and co-NP hard. So we have an upper and a lower bound of complexity here. For the last result about, the last hardness result about limit configurations, we changed the concept of a property. So now a property of limit sets is just any collection of limit sets. And we'll abuse notation and pretend that P is a logic formula even when it isn't. So F models P basically means that F has the property P, even if P is an abstract object and not a formula. And we say that a property P is effectively non-trivial if and only if there's an algorithm that, well, basically produces examples and counterexamples of that property in polynomial time. So formally, algorithms that, given an integer n in unary, produce an example and a counterexample of the property with n nodes each. And that does that in polynomial time. So an example of such a property is being a singleton, having exactly one limit configuration, which is a relevant property because this means that all the runs of the system end up in the same configuration that loops. Well, every effectively non-trivial property of limit set is p-space hard. And it is even p-space hard if we allow non-deterministic automata network as input. So on one hand, we are only dealing with limit sets instead of limit graphs, but we allow the input to be non-deterministic. So in particular, this means that this result do not rely on the specific shape of a transition graph that we had up to now. So this is our only result for now about non-deterministic automata network, but still, as we explained, it is a relevant one because it shows that having a single limit configuration is already p-space hard. So, as a conclusion, we saw that automata networks are graphs whose nodes evolve with time according to what they read from their inbound neighbors. We worked on both transition graphs and limit sets of these automata networks. We've just explained that effectively non-trivial properties on limit sets are p-space hard even on non-deterministic automata networks. We've shown that counting limit configurations is often p-space hard on deterministic networks, and even when it's not p-space hard, it's still at least co-NP hard, depending on what you call counting. And last but not least, first-order properties of transition graphs are NP hard or co-NP hard, or they are trivial. And finally, first-order properties of limit graphs are also either NP or co-NP hard. Thanks for following, and have a nice day. Bye.